so this is the first example for independent samples t-test. We have two samples. The research hypothesis is basically that people are going to recall more things if they are hypnotized. So they are shown a video of a supposed robbery, and then they answer 30 questions, and I'm assuming they're going to see how many they get correct from the details of the video. So one sample is going to get hypnotized, and the other sample is not going to get hypnotized. But notice that they're not the same units in these two groups. That's why they are independent samples. So remember that independent variable, it's always going to be categorical or nominal. So it's going to have in Jamovi the little 3-circle diagram, Venn diagram. So either they get hypnosis or they get no hypnosis. They just answer the questions. The dependent variable, that's usually the outcome. So we're manipulating this variable. Either we give them the hypnosis or not. And we want to see what causes, what's the reaction of us doing this. And that's usually going to be measured in a numerical form. So here it's going to be the amount recalled correctly. What's nice about the independent samples is they usually, at least for the handwritten problems, is that they usually have like this little summary statistics where they give us the sample mean, the sample size, and then in this case they gave us the variance. So if we actually wanted to find the standard deviation, which would be just as, we would take the square root of 15.50 and the square root of 34.30. So for hypnosis, the standard deviation would be 3.94, and for no hypnosis, the standard deviation would be 5.86. Yeah. Okay. I also did a little box plot in Jamovi just to look at the two variables. Notice how I have the hypnosis score. So this is going to be our continuous variable, which is also our dependent variable. And then here we have the nominal variable, which is in the independent variable, whether they had hypnosis or no hypnosis. And we can see the range for no hypnosis is wider. Remember, this one is the medium. They're not that different. We could actually just go ahead and find the descriptives. That would also help us. We can see the range here, not as wide for hypnosis. So I see a difference here, but the question is, and the reason why we're going to do our statistical test is to be able to say, is there a statistically significant difference? Okay, so first we're going to do our pair of hypotheses. No alternative. Because we have two samples, it's going to be mu1 minus mu2 equals 0. Mu1 minus mu2. And here they didn't really give us a direction. So we're going to go with two tails, so different. We want to see if there's a difference between hypnosis and not hypnosis. But they didn't tell us we expect one of them to recall more than the other one. We're going to find our critical value. For our critical value, we need our degrees of freedom, n1 minus 1, plus n2 minus, that should have been a minus 1. So my degrees of freedom, let me show you where the n's are. They're going to be here, 17 and 15. So when we do this calculation, it's actually 30. Our alpha is going to be 0.05. And remember, it's a two-tail test. How do I know this? I know it from here, from this symbol. If it's different, that means that our test is two-tail. So let's go to the table. We are in our t-table. We're going to do two tails. It's going to be 0.05. Let me draw the line all the way to the bottom, and then I'll move it up a little bit. So our degrees of freedom are 30. So our critical value is going to be 2.042. So t crit is plus minus, because it's a two-tailed test, 2.042. From here we could what we need to do is find our t-obtain. Okay, so this is also our t-obtain. We need both sample means here. This part of the equation, by definition or by default, you know that from the null hypothesis, the difference between these two is going to be 0. So it's just a big fat 0. There's actually textbooks that don't put that piece of the equation in there. They just use the half to the left. But by definition, it's just a 0. So let's plug in everything here. It's going to be 23 minus 20.8 minus 0 divided by a giant square root. 15.5 divided by 17 plus 34.3 divided by 15. Oops, this looks a little ugly. Okay. In the numerator, I'm going to have 2.20. When I do this piece and then this piece, I get still my giant square root. So 0.91 plus 2.29. Okay, I'm going to go over here. I kind of ran out of space. So 2.20, all of this divided by 3.2, the square root of that, 2.20. When we actually take the square root of that, it's going to be 1.79, 1.23, roughly. I say roughly because the rounding is a little different in Jamovi. Now we're going to do our confidence interval. So we're going to do the margin of error first. That's what the E stands for. And it's usually the T critical, and then it has like a square root of something, like the standard error of something. So our T critical was 0.42 times, I'm going to put parentheses, just $15.5 divided by 17 plus 34.3 divided by 15. We kind of already know what this is. We already did it here. There it is. So it would be 2.042. So it's nice if we have to do the whole problem, because the confidence interval is really easy to do. We only have to do it once. That's what I'm trying to say. 1.79. Let's go back here. So E, which is my margin of error, this is going to be 3.65. And then from here, we can put it into our confidence interval. Notice how in the middle of the confidence interval, now we don't just have a mu anymore. We have mu1 minus mu2. So it's a confidence interval for the difference. Okay, so let's do our little notation. So it's going to be 23 minus 20.8 minus 3.65, mu1 minus mu2. And it's the same thing. I'm going to put parentheses here because it's cleaner that way. So 20 minus 20, 23. 23 minus 20.8 plus 3.65. We kind of already did this as well when we did the t-obtain. So I know is this value 2.20. So here we have 1.45, mu1, mu2, and on this side is going to be 5.85. So that is our confidence interval. Okay, so now let's look at the output from Jamovi. So notice it's an independent samples. This is our t obtained. This is our degrees of freedom. This is our p-value. This would be the difference between these two sample means. This is our x bar essentially. This is our S, standard deviation. This is just our sample size. This one over here. Confidence interval, you know, it's a little off, but the direction is still the same. The conclusion would still be the same. We also have our p-value. Normally what we do is that we compare our p-value to our alpha. So alpha was 0.05. We know also that we need to make sure that when the alpha is 0.05, this should be 95. If it was 90, then the alpha would be 0.1 and so on. There's a relationship there. If our p-value is greater than our alpha, which it is here, this is greater, we do not reject the null hypothesis. Do not reject the null hypothesis. We also have, we are doing a two-tailed test. We know that our t-crit was 2.042, and over on this side it was negative 2.042 t-crit. Our t obtained was, it was 1.23. So this is our t obtained. It is not on the rejection region, so we also decide to not reject the null hypothesis. Okay, from here I have all the information that I need. I usually start with the name of the test. So I did an independent samples t-test, the significance level that I use, kind of a little story about what were you comparing, like what were the two different samples that you were looking at. We decided not to reject the null hypothesis, so that's the next thing we have to say. Do not reject the null hypothesis. Whenever we do not reject the null hypothesis, it also means that it was not statistically significant. So that's the next thing that we say. You can put the means and standard deviations for the two samples that you're comparing. Here it's going to be your degrees of freedom, your t obtained, the p-value, and you will get this one from software, and then the confidence interval over here.